We are going to do a recap of lessons 10 and 11 if you're following along in your workbooks with this. So the first one that we'll talk about is different forms of equations and some information that we can get from those. So we'll look at some equations in both standard form, you can see up there at the top, and slope-intercept form, you can see there at the bottom. Let's start out with standard form and let's look at this information here. So we know that from this situation, an athlete wants to burn 700 calories a day by running and swimming, and he burns 17.5 calories per minute of running and 12.5 calories per minute of freestyle swimming. And we'll let X represent the number of minutes of running and Y the number of minutes of swimming. And so to represent the combination of running and swimming, that would let him burn 700 calories. This would be the equation that we would write. A couple of things before we get into reviewing how to find the X and Y intercept. In a situation like this, we talked about this in class, not this particular situation, but the more minutes he runs, the fewer minutes he has to swim to meet his goal. So in other words, as X increases, Y decreases. And so if we're picturing this, what the graph of this would look like, it would be a slant down from left to right. So I should be thinking right now that the slope is going to be negative. So if he only runs and doesn't swim, how many minutes would he need to run? This is asking you to substitute 0 for Y because he didn't swim and Y was swimming, and find X. So you can see the process of us doing that. This is asking you to find what the X-intercept would be. So on a graph, this combination of times is the point 40, 0, the X-intercept. And then over here, you can see if he only swims and doesn't run, how many minutes would he need to swim? In this case, we would substitute 0 for X and solve for Y. And on a graph, this combination of times would be the point 0, 56, or the Y-intercept. I wanted to put this example up here because some of us are struggling with what those values mean. And so I wanted to give you just one more real-life example to kind of picture as you're thinking about Y when we're talking about the X-intercept, the Y value is 0. Or when we're talking about the Y-intercept, the X value is 0. So just take a minute to process what you're seeing there. The other thing that we might want to do is if we know a given value of X. So for example, he ran for 15 minutes or 20 or 30, then we might want to know, well, what would Y be in that case? And so let's practice rearranging this equation to solve for Y. So I'm just going to rewrite my equation. Variables would be great. Okay, so I would like to solve for Y. I'm going to start just by subtracting this whole piece here. And whatever I do on the left, I need to do on the right also. So then what I'll be left with is 12.5 times Y is equal to a negative 17.5x plus 700. And now to finish, I would want to divide each side by 12.5. It's really important over here to remember that I have to divide each term by 12.5. But now I have just Y on the left, and I have a negative 1.4 when I do that division times X plus 56. Now, one thing should already stand out to you, and that's that we see that 56 is the Y-intercept and 56 in my rewritten equation. Another thing that you should remember is if I graphed either one of these equations, this one or the one I started with, they're equivalent. So the graph would be the same line. And this is slope-intercept form. So slope, or so the y-intercept is this 56, and that means the slope of our graph is a negative 1.4. And we already said when we got started that thinking about what this graph should look like, it would have a negative slope. So let's now talk about slope-intercept form using the same equation. So here's the rewritten equation that we just figured out on that slide before. And that coefficient of x, the negative 1.4, is the slope of our graph. So this means that as x increases by 1, y falls or decreases by 1.4. For every additional minute of running, he would swim 1.4 fewer minutes if we're thinking about the context. This constant term, 56 there at the end of our equation, tells us where the graph intersects the y-axis. And in this situation, that's the number of minutes the athlete would need to swim if he doesn't do any running in order to meet this constraint of burning 700 calories. And then finally, you can see these equations written as how you will generally see standard form, that ax plus by equals c. That doesn't need to be in there. Where a and b are numbers, c is a number, and then you have those two unknown variables, x and y. And like we were saying on the previous slide, if I made a graph, they would have the same solutions and the same graph.